Welcome to Deep Dive into Knowledge.
Welcome to Deep Dive into Knowledge. Tonight, we are going to explore something that lives quietly in the shadows of our collective imagination. We are looking at a phenomenon of the natural world that has been deeply misunderstood for generations. We're going to examine the true nature and the careful physics of quicksand. If you grew up watching films or reading adventure stories, you likely have a very specific image in your mind. A person steps into a patch of innocent-looking sand. The ground seems to pull them down. They struggle. The sand rises to their waist, their chest, and then they disappear completely beneath the surface. For decades, this image has been presented to you as an accepted reality of nature. I remember being a child, sitting in front of the television watching explorers in jungle serials or desert epics meet this exact fate. I remember genuinely believing that avoiding these invisible, bottomless pits would be a major daily concern in my adult life. It is a shared psychological quirk of an entire generation, this quiet fear of the earth simply opening its jaws. But the truth of what happens beneath our feet is far more fascinating and entirely different from the stories you may have been told. Tonight, we will examine the precise physics of sand and water. We will explore how a solid surface can suddenly transform into a liquid, and why the human body interacts with this mixture in a way that makes sinking completely an absolute physical impossibility. We will uncover how specific geological conditions create these hidden pockets in nature, from coastal beaches to desert lakes. And we will help you understand the true danger of quicksand, which is not about being swallowed by the earth, but rather about the immense physical forces that trap a person in place. This is a journey into the mechanics of the natural world. It is about how a tiny shift in stress can change the physical state of the ground, increasing its downward flow by a factor of 1 million. It is a lesson in why we must remain calm when nature surprises us, and a masterclass in how understanding the rules of physics can literally save your life. To begin our journey tonight, could you explain the fundamental physics at play here? What exactly happens at the microscopic level when ordinary sand and water combine to create a surface that behaves like a living trap?
To really get to the bottom of this, we have to strip away the cinematic mythology you just described. We need to look at the language itself first.
Right.
The word quicksand is actually quite revealing if we look at its history. In modern times, we associate the word quick with speed. We think of something happening rapidly.
Like moving quickly, yes.
Exactly. But the origin of the word comes from ancient English, where quick simply meant alive or moving. When you read older texts that refer to the quick and the dead, they are distinguishing between the living and the deceased. So quicksand is quite literally living sand.
Living sand.
Yes, it's sand that appears to possess a sudden, startling animation.
That perfectly captures the illusion of it, I think. It brings to mind the quick of a fingernail, that sensitive living tissue beneath the surface. It implies that the ground itself has suddenly animated or awakened the moment you step on it.
It does. And to understand how the ground comes alive, we have to look at what it's actually made of. True quicksand isn't a unique type of mineral.
So it's not a specific kind of sand?
No, not at all. You can't take a bucket of quicksand, dry it out, and find some special treacherous element left behind. It is what we call a colloid.
A colloid. Let's break that down for the listener.
A colloid is a mixture where entirely different phases of matter are suspended together. Think of everyday items like milk or mayonnaise or even fog.
Right.
These are all colloids, where tiny particles of one substance are scattered evenly throughout another. In the case of quicksand, we have fine granular material, which could be sand, silt, or clay, suspended perfectly within water.
Okay, so it's a suspension.
Exactly. But it isn't just a matter of throwing some water onto sand. It is a highly specific mathematical ratio. The water must account for roughly 20 to 40% of the total volume of the mixture.
So it's a very delicate balance. I mean, if there's too much water, you just have a muddy pool.
Precisely.
And if there's too little, you just have damp ground. The magic or the danger lives entirely within that 20 to 40% window.
The ratio is everything. And the clay content is also incredibly important here. The clay provides a slight cohesion, and it helps trap the water evenly throughout the structure.
So the clay is sort of holding it together.
Yes. To see why this specific ratio is so profound, we have to zoom in. We need to examine the ground at a microscopic level.
Let's do that.
Think about ordinary dry sand on a beach. If you look closely at dry sand grains under a microscope, they aren't perfectly smooth spheres.
Right, they're not like little glass marbles.
No, they are jagged, irregular little fragments of quartz and rock. When you step on dry sand, those jagged edges lock together. They rest against one another, and the empty spaces between them are filled only with air.
Okay.
Your body weight pushes those grains downward, forcing them to interlock even more tightly. This creates what physicists call intergranular friction.
Intergranular friction.
Yes. The more pressure you apply, the more the grains resist moving past one another. The sand provides a stable, solid surface that easily supports your weight.
It's like a three-dimensional jigsaw puzzle, isn't it?
That's a very good way to picture it, yes.
The harder you press down on the pieces, the more the jagged edges bite into one another, bracing against the pressure to hold us up. I suppose this is why we can run along a dry beach without sinking more than a fraction of an inch.
Exactly. But when water enters the equation in that perfect 20 to 40% ratio, the entire physical structure changes.
Because the water displaces the air.
Yes. The water displaces the air in those microscopic gaps. Now, water is an exceptional lubricant. It coats every single jagged edge of those sand grains. When the sand becomes fully saturated, the water pressure actually pushes the grains slightly apart. They are no longer resting their full weight on one another.
So the friction is gone.
The friction that previously held the ground together is drastically reduced. The sand particles are now suspended in the fluid, barely touching.
Okay, so this brings up a very practical question for me. If I'm walking along the shoreline at low tide, right at the water's edge, I'm stepping on very wet, highly saturated sand. But the ground there feels incredibly firm. In fact, wet sand near the waves is often much harder and easier to run on than the dry, loose sand higher up the beach. How does a normal, firm shoreline differ from this delicate colloid trap we're discussing?
That's an excellent point. On a normal wet beach, the sand is deeply compacted. The ocean waves have repeatedly washed over it, lifting and dropping the grains, settling them tightly together.
So they are already locked in place.
Exactly. The water simply fills the tiny remaining voids between grains that are already in firm, locked contact. But in quicksand, the mixture is entirely undisturbed and uncompacted. It exists in a bizarre intermediate state of matter. It is a shear-thinning, non-Newtonian fluid.
A non-Newtonian fluid. Let's unpack that concept, because the physics of it is really the absolute core of the illusion.
Yes, it is.
We hear that term thrown around in science classrooms, but how does it actually behave in the wild?
To understand a non-Newtonian fluid, we have to contrast it with a Newtonian fluid, like pure water. If you agitate a glass of water or strike its surface, its viscosity, its thickness and resistance to flow remains completely constant. Water always behaves like water, regardless of how much force you apply to it.
Right, hitting water doesn't make it thicker or thinner.
Precisely. But a non-Newtonian fluid defies this rule. Its viscosity changes depending on the stress or force applied to it.
And quicksand is specifically shear thinning.
Yes, shear thinning. This means that when it is left entirely alone, completely undisturbed, the sand and clay particles form a fragile, interconnected lattice.
The lattice?
Yes, the clay acts almost like a gentle glue, holding the water and sand in a highly structured, gel-like state. It looks solid. It reflects light like a solid. It behaves like a solid.
It's a house of cards. It is a solid structure, just waiting for a physical disruption.
It's waiting for a change in stress, exactly. And it requires almost nothing to trigger the collapse.
Really? How little force are we talking about?
A stress change of less than 1%. The simple, gentle impact of a human footstep is enough to shatter that delicate, microscopic lattice.
Wow. Just 1 footstep.
The moment your foot adds that tiny fraction of additional weight, the fragile bonds break, the loose packing arrangement is destroyed, the structure completely collapses.
So the viscosity of the mixture violently drops.
Violently drops. Within a fraction of a second, the water and the loose sand grains suddenly slip past one another with zero resistance.
That's incredible.
To put this in a mathematical perspective, that tiny shift in stress increases the downward flow speed of the ground by a factor of 1 million.
1 million times faster.
1 million times more fluid than it was a second before. You step onto what appears to be solid earth, and instantly the ground beneath your boots becomes a deep, heavy liquid.
Which perfectly explains the terrifying sensation of being swallowed by the earth. The ground literally turns to a deep soup beneath your feet.
It does.
But wait, hold on. This brings us to the core contradiction of the entire phenomenon.
Right.
If the ground turns to liquid so completely and so suddenly, why is the cinema image, the person slowly disappearing completely beneath the surface, an absolute physical impossibility?
Yes, the cinema image.
If we are suddenly standing in a pool of liquid, Why don't we sink straight to the bottom like a stone?
Well, because of density. The cinematic image of a person disappearing beneath the sand ignores the most fundamental laws of fluid dynamics, laws that have been understood since ancient Greece.
By Archimedes.
Yes. To understand why you cannot sink completely, we have to look calmly at the mathematics of density and Archimedes' principle of buoyancy.
Let's walk through that calculation. It's fascinating to realize that the human body is inherently protected by its own physical makeup.
It really is. Let's begin with the human body. The density of an object determines whether it will float or sink in a fluid.
Okay.
Density is simply a measure of how much mass is packed into a given volume. If we take the average human being, our bodies are composed mostly of water.
Along with bones, muscles, fat, and air in our expanding lungs.
Exactly. Depending on body fat percentage and how much air is in your lungs at any given moment, human density varies slightly.
So it fluctuates.
Slightly, yes, from perhaps 0.95 to 1.05 grams per cubic centimeter. But when you average all of this out, the density of a human is reliably 1.0 grams per cubic centimeter.
So we have a biological density of exactly 1.0.
Yes.
And how does that compare to the liquid ground we've just stepped into?
This is where the physics of the natural world saves us. Quicksand is a mixture of water and heavy rock fragments. Even when it liquefies, it is incredibly dense.
Because of all the suspended rock.
Exactly. The measured density of a typical quicksand mixture is approximately 2.0 grams per cubic centimeter.
So it's exactly twice as dense as a human being.
Exactly twice as dense. Now, we apply Archimedes' principle.
Right.
Archimedes discovered that when an object is placed in a fluid, it experiences an upward buoyant force equal to the weight of the fluid it displaces.
Okay, so the fluid pushes back up.
It pushes up, yes. For an object to float, the buoyant force pushing up from below must equal or exceed the downward weight of the object itself.
That makes sense.
The mathematical rule is straightforward. If your density is less than the density of the fluid, you will float, just as a block of wood floats in a river.
So since human density is 1.0 and quicksand density is 2.0, we must be very buoyant.
You are remarkably buoyant in this mixture.
Think of it like stepping into a normal swimming pool. Pure water has a density of 1.0, and my body has a density of roughly 1.0.
Yes.
Because our densities are perfectly matched, I barely float. I mean, I have to tread water, keeping my lungs full of air just to keep my nose above the surface.
Right.
I displace almost 100% of my body volume to stay afloat. But if I transfer my body to a pool filled with liquefied quicksand, the math changes completely.
It does. Because the quicksand is twice as dense as you are, the fraction of your body that needs to be submerged changes. It becomes 1.0 divided by 2.0.
So 1/2.
Yes. You only need to displace 50% of your body volume to generate enough upward buoyant force to hold your entire weight.
Meaning I will only sink halfway.
You will sink until you have displaced your own weight in the heavy sand mixture. Because the fluid is so exceptionally dense, this happens exactly when the sand reaches your waist.
Or perhaps your lower chest, depending on your build.
Exactly. At that exact moment, the upward buoyant force perfectly equals the downward pull of gravity. You achieve a state of physical equilibrium.
Got balance.
You become a floating object permanently supported by the dense fluid beneath you. The laws of physics dictate that you simply cannot sink any further.
It's just a hard rule of the universe.
It is. Complete submersion defies the fundamental mechanics of the universe.
It's a profound comfort to realize that the universe mathematically prohibits us from sinking. I mean, it ruins a century of Hollywood set pieces, but it's deeply comforting.
Quite right.
And this isn't simply theoretical physics, is it? This density calculation has been rigorously tested and validated in laboratory conditions.
It has been conclusively proven. Researchers at the University of Amsterdam conducted an elegant set of experiments to permanently settle this question.
What did they do?
They sourced fine sand and clay, mixing them with water to create highly accurate artificial quicksand in the laboratory.
So they built a controlled environment.
Yes, perfectly matching the composition and the 2.0 density of natural deposits found in places like Iran's Namak Lake.
Okay.
They then took small aluminium beads to act as stand-ins for human victims. Now, solid aluminium metal is quite heavy. It has a natural density of 2.7 grams per cubic centimeter.
Which would normally sink.
It would. But they engineered these specific test beads, hollowing them out slightly, so they possessed an overall density of exactly 1.0 grams per cubic centimeter.
Perfectly mirroring human density.
Exactly. So they essentially created miniature metallic human stand-ins.
Yeah. What happened when they placed them in the mixture?
They placed these human density beads on the surface of the artificial quicksand. When the mixture was left completely undisturbed, the beads simply rested on the surface.
Supported by the gel-like structure we talked about earlier.
Supported by the solid, gel-like structure of the non-Newtonian fluid. But the researchers needed to simulate the chaotic movement of a panicked person.
Right, because nobody stands perfectly still when the ground gives way.
Exactly. So they began to shake the container, inducing the exact physical stress required to liquefy the sand.
Replicating a person frantically kicking and thrashing in the heavy liquid.
The quicksand instantly liquefied. The beads began to sink. But the scientists observed exactly what Archimedes would have predicted thousands of years ago.
They only sank halfway.
With gentle shaking, the beads partially sank but quickly stabilized. And even under continuous, aggressive shaking to simulate absolute human panic, the beads never sank completely.
Wow.
They simply bobbed in the heavy liquid, perfectly half-submerged. To confirm the physics, the researchers then tested beads that were denser than 2.0 grams per cubic centimeter.
What happened to the heavier beads?
When the quicksand was shaken, those denser beads sank entirely to the bottom. They proved beyond any doubt that while heavy objects like a dropped watch or a heavy stone will sink, an object with human density will never vanish beneath the surface.
Okay, I have to push back here.
Please do.
We've established that the ground liquefies, and we've established the math proving we cannot drown in the sand.
Yes.
But people do perish in these environments. It remains a genuine lethal threat in the natural world. I've read the news stories of rescues gone wrong or people getting trapped while out hiking near estuaries.
That is undeniably true.
So, if we aren't sinking to our doom like in the movies, what exactly makes quicksand so dangerous? What is actually killing them if they aren't drowning in sand?
The danger of quicksand has nothing to do with sinking. It has everything to do with being completely, rigidly immobilized.
Immobilized.
Yes. The terrifying part isn't the initial liquefaction. The terrifying part is the aftermath, what happens to the internal structure of the mixture once you have sunk to your waist and the movement stops.
Ah, so the phase transition happens again.
It happens again, and it happens with brutal efficiency. Once you have triggered the liquefaction and sunk to your waist, you have completely disrupted the perfect suspension of the colloid.
The mixture breaks down.
It rapidly separates into its two distinct phases. The water, which is a lighter phase, rises toward the surface.
Leaving the sand behind.
And the sand, which is incredibly heavy, violently settles downward. And because your legs are now submerged deep within the mixture, that heavy, wet sand tightly packs itself entirely around your legs and feet.
It effectively casts your legs in solid rock.
It forms a densely compacted sediment around your limbs. The volume fraction of the sand becomes extremely high, meaning there is almost no free-flowing water left between the grains surrounding your feet.
It just squeezes all the liquid out.
Yes. It achieves a massive density and an enormous unyielding viscosity. You are no longer floating in a liquid suspension. You are encased in deeply compacted earth. And when a person realizes they are trapped, their immediate human instinct, driven by millions of years of evolution, is to simply lift their leg out.
It's the natural response, yeah.
We assume that if we pull hard enough, we can break free. But there is a hidden mathematical force working against us beneath the surface, isn't there?
There is, and it's a force of staggering magnitude. When your foot is encased in heavily compacted wet sand and you attempt to pull it upward, you are not simply lifting the weight of the sand on top of your foot.
What are we fighting against then?
You are fighting against a deeply powerful physical phenomenon, a vacuum.
Let's break down the exact mathematics of that vacuum. How does it form just by me trying to lift my leg?
Imagine your foot buried deep in the compacted sand. The wet sand is molded perfectly, tightly around the sole of your shoe.
Right.
There is no air, and there is no free-flowing water touching the bottom of your foot. If you try to pull your foot directly upward, even slowly, you are attempting to create an empty space where your foot just was.
But nature abhors a vacuum.
Exactly. For your foot to move upward, something must immediately flow into that empty space beneath it to relieve the negative pressure.
And the compacted sand is far too dense to flow into that space.
The sand is locked firmly in place. The water cannot easily penetrate the tight gaps between the sedimented grains to reach the void beneath your foot.
So the suction is created.
As you pull up, you generate an intense negative pressure. The entire weight of the surrounding atmosphere and the heavy, saturated earth is pressing down while you are trying to tear open a vacuum below.
That sounds incredibly difficult to overcome.
The researchers in Amsterdam calculated the precise force required to achieve this extraction. If you attempt to pull your foot straight out at a speed of just 1 centimeter per second, you must overcome roughly 100,000 pascals of pressure.
Wait, 100,000 pascals?
Yes.
For someone trying to visualize that abstract number, what is the physical equivalent of that kind of force?
It is the exact equivalent of the force required to lift a medium-sized car off the ground.
A car. So when my brain is panicking and telling me to just yank my leg out, I'm essentially trying to deadlift a vehicle with one ankle.
Yes. It is a biological impossibility. The muscles in the human back and legs simply cannot generate that kind of leverage or power.
You just can't win against that kind of pressure.
You cannot outpull the vacuum. In fact, if a rescuer were to tie a rope to you and attempt to rapidly drag you out with a vehicle or a winch, the force required to break the vacuum is so immense that it could cause catastrophic physical trauma.
Tearing muscles and ligaments.
Tearing muscles, ligaments, and dislocating joints long before the sand yields.
Which makes the natural human reaction to this event incredibly tragic. Our immediate instinct is a fight-or-flight response. We panic, we jerk our limbs, we pull upward with all our might, we thrash against the confinement.
And that frantic struggle is the absolute worst possible reaction you could have. It guarantees you'll remain trapped.
Because we're fighting the vacuum.
When you pull violently upward, you cannot break the vacuum, but you do exert immense shear stress on the surrounding sand,
causing more problems.
That violent stress induces further liquefaction around the edges of the compacted zone. You tire yourself out incredibly quickly, burning massive amounts of caloric energy, straining your cardiovascular system, and ultimately achieving nothing.
You might even sink a little deeper into the newly liquefied edges before it instantly compacts again.
Exactly. You exhaust yourself fighting an unwinnable war against atmospheric pressure.
Okay, so I can't sink, but I can get trapped with the weight of a car holding me down. Where am I most likely to accidentally step into this? Is this just a desert oasis problem like in the movies, or are these invisible traps closer to home?
They are often much closer than we think.
How does water find its way into the sand in such a perfect, lethal ratio, without giving any visible warning on the surface?
Quicksand is entirely invisible until the moment of interaction, which is why it requires very specific, hidden geological conditions to form. There are 3 primary mechanisms in nature that create these hidden pockets.
Let's outline them calmly, beginning with the most common natural formation.
The first is the artesian spring,
an upward-flowing underground water source.
Imagine a deep underground reservoir of water, highly pressurized by the weight of the rock above it. This water seeks the surface, finding a path upward through a deep layer of loose sand.
Okay.
Because the water is flowing upward, directly against the pull of gravity, it possesses physical force. It acts almost like an invisible fountain beneath the earth.
Pushing up on the sand.
The upward pressure of the water perfectly counteracts the downward weight of the sand grains. The grains become suspended, gently floating in the upward current, just barely touching one another.
They form that perfect fragile lattice we discussed earlier.
Yes, and the surface looks perfectly dry and stable. A crust of dry sand might even form on top, completely masking the danger below.
So there's zero visual warning.
None at all. But beneath that thin crust, the artesian spring has created a deep column of suspended, zero-friction sand. This frequently happens near riverbanks, the shores of deep lakes, and hidden marshes where the water table is high.
And then you take a step.
You take a step, your weight breaks the crust, you disrupt the delicate upward pressure equilibrium, and the solid column instantly collapses into a flowing liquid.
That covers the slow, steady pressure of a spring. But what about places where this happens on a massive scale? I've seen footage of entire streets turning to liquid.
That is the second mechanism, known as seismic agitation. This happens during an earthquake.
Ah, I see.
In areas where the soil is highly saturated with water, perhaps a city built on reclaimed coastal land, a deep river delta, or an active fault line, the ground normally supports immense weight, even the weight of buildings, through that compacted intergranular friction we discussed.
Right, the grains are locked together.
But when an earthquake strikes, the sudden, violent vibration acts as an overwhelming stress change on the entire landscape.
The shaking violently breaks the friction between the millions of grains all at once.
Instantly. The entire waterlogged landscape liquefies in a matter of seconds. The soil loses all bearing capacity.
That must be terrifying to witness.
It is a terrifying phenomenon known as soil liquefaction. Solid ground suddenly behaves like a dense soup. If you look at historical footage of the 1964 earthquake in Niigata, Japan, you can see intact apartment buildings that simply slowly tipped over, sinking into the earth because the ground beneath them turned to liquid quicksand.
So an earthquake can essentially turn an entire city block into quicksand.
Exactly. It is a temporary state lasting only as long as the vibration and the immediate settling period, but it demonstrates how quickly saturated sand can transform when agitated.
So if earthquakes are sudden and massive, what about places where this is a daily, invisible threat? That brings us to the coastline, doesn't it?
The tidal trap is perhaps the most dangerous of the three because of where it occurs. On certain coastal beaches, estuaries, and sweeping tidal flats like Morecambe Bay in the UK, for example, you have a deep layer of sand.
Which gets saturated twice a day.
As the high tide washes in, it entirely saturates the beach. When the tide recedes, gravity normally pulls the water down deep into the earth, draining the sand and leaving it firm.
But something interrupts that draining process.
In these specific locations, there is a hidden layer of impermeable clay lying horizontally directly beneath the sand.
An invisible barrier preventing the water from draining away.
An absolute barrier. The water attempts to drain downward, but it hits the clay layer and stops. It pools inside the sand, trapped between the clay below and the surface above,
Creating the perfect ratio.
The sand remains deeply saturated, suspended in the trapped water, entirely unstable. As you walk across the tidal flat, the beach looks perfectly normal.
Until you step on it.
But when you step over a hidden clay basin, the stress liquefies the trapped water and sand, and you sink into the coastal trap.
In this specific environment, the coastal tidal flat, is where the true danger of quicksand reveals itself.
It is.
If sinking doesn't kill a person, what are the genuine hazards of being completely immobilized in these landscapes? What is actually happening in those tragic news stories?
The true fatalities of quicksand are entirely environmental. The sand merely holds you. The environment becomes the executioner.
Let's explore that. What happens if you are trapped in an arid region?
If you are trapped in an arid region, such as a desert lakebed or a dry oasis, the immediate danger is exposure. You are locked in place under a blazing sun, unable to seek shade or shelter.
Because you simply cannot move.
Without intervention, a person will succumb to severe dehydration, hyperthermia, and sunstroke within hours. The body simply cannot regulate its internal temperature under direct sunlight while enduring the extreme physical exhaustion of being trapped.
The sun and the heat become lethal.
But the most tragic and frequent fatalities occur in those coastal tidal traps we just described.
Because of the ocean.
When a person is immobilized on a tidal flat, they are racing against the moon. They are held fast by the vacuum of the heavy sand, completely unable to free themselves. And slowly, inexorably, the high tide begins to return.
Water comes back.
The water creeps back across the flat. The victim is trapped at waist height. The water rises to their chest, then to their neck. It is the rising tide that causes drowning, not the sand itself.
The sand merely ensures they cannot walk away from the approaching water.
Exactly. It holds them in place while the environment shifts around them.
That is a deeply chilling reality. The sand holds the victim while the ocean returns. It places a profound urgency on the need to escape.
Tremendous urgency, yes.
We've established that pulling upward with brute force is mathematically impossible, requiring the strength to lift a car. So we have to pivot to the solution.
We do.
How can a human being, trapped in this massive vacuum, overcome these forces using only their own body and mind? If I'm stuck out on a tidal flat, what is the science of escape?
The science of escape relies entirely on counterintuitive mechanics. It requires you to override every kinetic-driven instinct your brain throws at you.
Which is incredibly difficult to do in a survival situation.
It is. The very first step is entirely psychological. You must immediately recognize that you are not going to sink out of sight. You must force your breathing to slow down, and you must absolutely cease all frantic thrashing.
You have to surrender to the initial sinking, trusting Archimedes' principle.
You let the sand settle at your waist. You take a breath. Once you have stabilized mentally, the physical work begins.
What is the first movement?
The first physical movement is to slowly lean backward. This is incredibly difficult to do both psychologically and physically because the wet sand is tightly packed around your lower back and legs.
But you must force yourself to lie back.
You must slowly lean your upper body backward onto the surface of the quicksand, spreading your arms wide.
You are essentially attempting to mimic the posture of floating in a lake. You're changing your geometry.
By leaning backward and spreading your arms, you are radically increasing your surface area. You are taking the downward force of your body weight and distributing it across a much wider expanse of the sand.
Dispersing the weight.
This reduces the pressure per square inch, which ensures you will not sink any deeper during the extraction process. You transform yourself from a vertical weight plunging downward into a horizontal object resting gently on the surface.
Okay, so my upper body is floating, but my legs remain encased in the compacted sediment, locked securely in the vacuum. How do we break the vacuum without exerting the pressure of 100,000 pascals?
We defeat the vacuum not with power, but with patience and precise fluid dynamics. You cannot pull the leg out, so you must intentionally change the state of the sand around the leg.
How do we do that?
You must introduce water back into the compacted sediment to re-liquefy it. To do this, you perform a technique we can call the slow pedal.
The slow pedal. Describe the precise mechanics of this movement.
While lying horizontally on your back, you begin to move your trapped legs. But the movement must be incredibly slow, almost imperceptibly slow.
How slow are we talking?
You attempt to move your leg in a tiny circular pedaling motion, moving only a fraction of an inch at a time. The slowness is the absolute key to the entire operation.
Why must it be so extraordinarily slow? If I move faster, wouldn't I create a wider hole to escape from?
If you move faster, you create violent shear stress, which instantly recompacts the sand and tightens the grip. Fast movements act as an impact, solidifying the non-Newtonian fluid.
So speed is the enemy here.
But if you move with deliberate, agonizing slowness, you gently push the heavy sand grains aside just a millimeter or two without triggering the compaction.
Because you're gently navigating the grains rather than forcing them.
Exactly. Because you are moving slowly, you allow the ambient water in the upper layers of the quicksand the time it needs to trickle down into the tiny gap you have just created.
You are manually carving out a microscopic channel for the water.
You are coaxing the water downward into the void. As the water trickles down around the calf, down toward the ankle, and finally to the sole of the foot, it begins to lubricate the compacted grains once again.
And that breaks the seal.
It gently breaks the vacuum. It turns the solid, rock-like packing back into a flowing, manageable liquid suspension.
That is brilliant.
You do this with one leg at a time, moving it in tiny, patient circles, allowing the water to seep deeper and deeper. As the leg becomes fully lubricated, you can slowly, horizontally extract it to the surface.
And then you move to the other leg.
And then you must repeat the entire agonizing process with the other leg.
It's a process that goes completely against human nature. We want to conquer the trap with immediate, explosive strength. But escaping nature's trap requires patience over power.
A successful abstraction using this method is incredibly physically taxing. It requires supreme core strength and immense mental discipline.
Because you are fighting the urge to panic the entire time.
Working just one leg free through the slow pedaling method, gently allowing the water to penetrate the vacuum, can easily take over an hour of continuous, deliberate, tiny movements.
Over an hour? That is astonishing.
You must move centimeter by centimeter, trusting the physics, knowing that every slow movement introduces a single drop of water that weakens the Earth's hold on you.
Over an hour of painstaking, gentle movement. It is the ultimate test of psychological endurance. You are lying on your back, staring at the sky, slowly manipulating the water table beneath the earth.
And if you maintain that discipline, the physics will always work, the vacuum will break, the density will support you.
And you can pull yourself completely free.
You will slowly extract your legs, roll horizontally onto the firmer ground, and stand up safely. The escape is always possible, provided you respect mechanics of the fluid you are trapped within.
We've spent this time dismantling a terrifying cinematic myth. And in its place, we have uncovered a deeply complex, almost beautifully mechanical reality.
It is quite beautiful when you break it down into numbers and forces.
The interplay of water, quartz, friction, and density creates a phenomenon that is both captivating and perilous. Before we bring our journey to a close tonight, I would love to hear your final thoughts on what this phenomenon can teach us, not just about geology, but about how we interact with the world around us.
Well, if we connect all of this to the bigger picture, quicksand serves as a profoundly accurate reminder of how we relate to the natural world.
In what way?
Our deepest evolutionary instincts tell us that when we face a sudden danger in nature, we must immediately fight against it. We rely on sudden force, brute strength, and a panicked reaction to overcome the obstacle.
We treat nature as an opponent.
We treat nature as an opponent that can be wrestled into submission. But nature, especially in its most mechanical forms, doesn't yield to panic. It doesn't respect brute force because the forces of atmospheric pressure, vacuum, and density will always absolutely dwarf human strength.
So we must approach it with understanding instead of force.
Nature yields only when we take a moment to stop and to calmly understand its underlying rules. It yields when we learn its physics, respect its boundaries, and adjust ourselves quietly and patiently to its rhythms.
We have to align ourselves with the physics.
When we align our actions with the unbending laws of nature, rather than fighting blindly against them, the trap opens and we are allowed to walk away.
That's a beautiful way to frame it. Tonight, we have taken a gentle journey of the mind. We have looked into the shadows of a childhood fear, the terrifying image of the earth opening up to swallow us whole. And step by step, through the careful application of logic, mathematics, and observation, we have dismantled that fear. We have replaced the myth not with a lack of danger, for the natural world will always command our utmost caution, but with a deep, abiding respect for the sheer mechanical power of water and earth. The physics of our world are not malicious, they are simply absolute. And once we understand those absolutes, we navigate the world with a quieter, more confident step. Before we close, it's fascinating to think how this exact physics is being used to save lives today. Engineers are currently looking at non-Newtonian fluids, very similar in behavior to what we've discussed, to create liquid body armor. Imagine a fluid that flows easily when you move slowly, but instantly hardens into an impenetrable shield the moment it is struck by a high-velocity impact. It's the same principle that traps a foot in the sand, being harnessed to protect human life. The next time you walk along a shoreline or near the quiet edge of a marsh, you might pause and look down at the damp sand beneath your feet. You might reflect on the delicate, invisible balance of microscopic sources resting quietly just below the surface, the millions of jagged grains, the lubricating water, the suspended tension waiting for a single shift in stress. The ground is a living thing, governed by elegant rules. Another fascinating exploration of our hidden world will come next time. I encourage you to carry these quiet reflections with you as you close your eyes. Until then, I wish you a peaceful night and a quiet mind. Good night.